Hello students, welcome to lecture 48 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on applications of transformational electromagnetics. So here is the lecture outline. We will first look into a few examples of transformational electromagnetics. We will see how we can have refraction without reflection, refraction at normal incidence, and how we can achieve cylindrical focusing, and after that we will move on to discussing some applications of transformational electromagnetics. We will discuss how invisibility cloaking can be obtained using optical metamaterials, and we will discuss very briefly about invisibility cloaks, which will be continued in the next lecture. So, let us look into some examples of transformational electromagnetics. So, the first example we will be handling today is refraction without reflection. So, you know that in normal scenario, whenever there is refraction, there is some light that is also reflected, right. So, in this particular case, we will see how you can develop material artificially that can give you refraction without any reflection. So, in this case, the desired optical trajectory is something like this. So, this is an optical material that implements these ray trajectories, which show you that there is refraction without any reflection, right, at a planar surface. So, these are the axes x3, x1 and x2, right. So, this is a geometrical transformation, okay, that will be implementing your reflection without reflection. So, this is basically a geometrical transformation that implements refraction without reflection. So, let us first begin with an initial homogeneous medium, say free space, with rays that basically follow parallel straight trajectories at an angle of theta 1, which is shown in this particular figure. So, you see these are basically parallel straight trajectories. Now, after you apply a geometrical transformation where you basically stretch the coordinate system by a scale factor s along this particular direction, right, x3, okay, for the positive half of this x3, that is x3 greater than 0. So, in that way, when you stretch, what will happen, you know, this stretching the coordinate system by a factor of s will cause the rays to change its slope. So, from this straight parallel slope, you will see that when you are stretching only the positive part of x3, you will see that the rays will develop a slope, and this angle can be marked as theta 2. Now, you will see that the desired refraction is basically achieved by choosing this stretching factor s, and that is basically a ratio of the initial and the desired slope. So, s is basically tan theta 1 by tan theta 2. Okay. Now, what is this transformation? The coordinate transformation can be written as, you know, there is nothing changing along the x1 direction. So, u1 will be same as x1, u are basically the new ones, right. u1, u2 and u3 are basically the new coordinates. Same, you have not changed anything along x2, so u2 will be same as old x2. However, along the x3 direction, stretching has happened. So, u3 is nothing but S inverse x3, right. So, this type of scaling of the Cartesian coordinate system, in which the directions of the axis do not change, will basically convert a cube into cuboid, right. So, you will basically see that this particular thing has now changed into cuboid, right. So, this has happened when you have stretched the coordinate system by a factor of s along only one direction. So, once you understand that these are my new axes, these were the old axes, you can always calculate the Jacobian matrix A. So, Aij can be given as dou ui dou xj, where I and j both can be 1, 2 and 3, and then you can calculate this because you already know the values. So, the Jacobian matrix can be now calculated. Okay. So, you see the stretching only happens along one direction. So, u3 will have some kind of, you know, role to play here, and finally you will get the matrix to be 1 0 0 0 1 0 0 0 S inverse, right. So, as you can see, this Jacobian matrix is basically a diagonal matrix where the elements are 1 1 and S inverse, right, and you can obtain the determinant of this matrix, determinant of A to be equal to S inverse. Okay. So, with that you can now correlate to the material property which can implement this kind of coordinate transformation, right. So, you can write epsilon naught inverse epsilon prime will be equal to mu naught inverse mu naught prime. So, epsilon prime and mu prime will be the new material permittivity and permeability, and that should be equal to modulus of determinant A inverse of that, and then you have A transpose A, and this we have already calculated that determinant of A is nothing but 1 over S. Okay. So, this will simply boil down to this equation. So, you have epsilon naught inverse epsilon prime which is equal to mu naught inverse mu naught mu prime. So, you can simply could have called this as mu prime by mu naught, that is also fine. Okay, that will be a 3 by 3 matrix, again a diagonal one. So, you have S 0 0 0 S 0 and 0 0 1 by S or S inverse. So, as I mentioned, these matrices epsilon prime and mu prime are basically diagonal. The isotropic material has principal axis pointing along the axis of the coordinate system. So, that is a good thing. And what are the values of the principal axis? You can see that epsilon 1 will be simply S times epsilon naught. Epsilon 2 will also be S times epsilon naught, but epsilon 3 will be 1 over S or S inverse times epsilon naught. The same thing will also apply for mu because they also have the same relation. So, mu 1 will be S mu naught, mu 2 will also be S mu naught, and mu 3 will be 1 by S times mu naught. So, next thing would be we have understood that the material properties are obtained. Now, some other parameters of this material should also be obtained, so that there is no reflection. So, that can be obtained by matching the phase shift that is encountered when a plane wave crosses this stressed free space segment with that encountered when the wave is basically transmitted through an unstressed segment filled with the new material, right. So, to determine the parameters, you got to basically consider 3 waves in turn, each with electric field along one of the 3 coordinates, right. So, we are now trying to do the matching of the phase shift, right. So, let us first consider wave 1, that is basically a plane wave that is traveling along the x3 direction with its electric and magnetic field in the x1 and x2 direction respectively. So, in that case you will see that the permittivity and permeability are basically epsilon 1 and epsilon 2 because it is along x1 and x2. So, epsilon 1 and epsilon 2. So, from that you can obtain what is your k, that is the wave number, that is omega square root of epsilon 1 mu 2. Okay. So, here you have epsilon 1 and mu 2. So, that goes in here. Okay. Now, you know that epsilon 1 is nothing but S epsilon naught, mu 2 is nothing but S epsilon naught. So, S will come out and this whole thing is giving you S times k naught, which is the vacuum wave number. Okay. So, this tells you that it is giving you a corresponding refractive index of N1, which is basically S. Okay. So, this is what is important, that you need to see that along the plane where the wave is incidenting, you actually see the same refractive index, right. So, in this case you are seeing that the wave is experiencing N1 equal S. So, you can say the phase shift that will be accumulated over a distance d will be simply given as S k naught d, okay, and that is the phase shift, and the impedance will be eta 1, that can be given as square root of mu 2 by epsilon 1, Now this is same as eta naught because they are both S times mu naught divided by S times epsilon naught. So S cancels out, so this is simply square root of mu naught by epsilon naught, which is nothing but eta naught. So there is no change in the impedance, and that will ensure that there is no reflection. Next we consider wave 2, that is taken along the x-ray direction again, but this time the electric and the magnetic fields are in x2 and minus x1 direction respectively. So in this case also, if you do the similar kind of analysis, you will see that the wave basically travels with a refractive index n2 which is equal to s, and it has also got an impedance eta 2 which is same as eta naught. Okay? And then we consider the third wave, that is wave 3, which will be traveling along x2 direction, and in this case the electric and the magnetic field will be in x3 and x1 direction respectively, right. So in this case you can approximate the permittivity and permeability to be epsilon 3 and mu 1. So that will give you the wave number equal to omega square root of epsilon 3 mu 1. Okay, so omega remains like that. Square root of epsilon 3 can be now written as S inverse epsilon naught. So this has to be there's a typo, it's epsilon naught, and mu 1 is S epsilon naught. So S basically cancels out and you get K naught. Okay, so that is basically giving you that the refractive index N3 is equal to 1. So in this case the phase shift will be simply K naught D, since there is no stretching in the x2 direction, okay, that is the direction of wave propagation in this case, and the impedance eta 3 will be simply square root of mu 1 by epsilon 3, right, and that is S eta naught. Okay, so there is a change in the impedance. So what we understood that using these results you can conclude that the final design is basically a piecewise homogeneous medium, where you have the free space in the left half plane, and then you have an anisotropic uniaxial material on the right half plane, which is shown here, right. So what is the property of this material? We have seen that N1, that is a refractive index along this direction, x1's direction, is S, N2 is also S, okay, that is the refractive index, and N3, that is along this one, it is basically 1. Okay. So in this case you can understand this is also having refractive index of 1, and in this direction it is again refractive index of 1. So when you look at the reflection which is coming from the boundary, okay, with the free space, that is basically your x1 x2 plane. Okay, so in x1 x2 plane you can see that the impedance that is there is basically same as that of the free space, because that's why we computed eta 1 and eta 2 separately, and both eta 1 and eta 2 came out to be same as eta naught. So there is no impedance mismatch, so there is no reflection, right. So these two factors distinguish refraction at the boundary of this synthesized anisotropic medium from a conventional refraction that takes place at a boundary of homogeneous and isotropic medium, right. So here what we have understood, that refraction is not accompanied by reflection, okay. So this is something completely new, and also the relationship between the angle of refraction and the angle of incidence is not governed by Snell's law here, it is rather given by this formula, which is S tan theta 2 will be equal to tan theta 1, right. So this is how you can actually achieve refraction without reflection, and that is from a anisotropic homogeneous material that will help you achieve that. So now let us look into the second example, which is basically refraction at normal incidence. Okay, so let us consider the design of an optical material that implements refraction at an angle theta at normal planar surface, right. So this is how the desired optical trajectory will look like. So you have normal incidence and then you are getting a refraction. So this type of refraction cannot occur at a boundary between two isotropic dielectric material, but this can occur at a boundary between an isotropic and an anisotropic material, right? So, to begin with, you take a pilot system of free space with ray trajectory that is shown as horizontal parallel straight lines, okay, and then you can basically implement the coordinate transformation that can give you this kind of refraction or bending of the rays. So, if you do that, you get u1 will be equal to x1, u2 will be equal to x2 plus s x3, okay, and then u3 remains same as x3, okay, and this kind of stretching is happening for when x3 is greater than 0, that is in the positive half plane, and s will now have the tangent dependency on theta, right. So, this will basically deflects the trajectory, and this is done as per the requirement and as desired by the shearing. So, you can actually do this by shearing along the x2 direction. So, you can see the coordinate system is basically sheared along the x2 direction, okay, like this by an angle of theta, and that is basically giving you that bending of the rays, and this is done only for the positive half plane of x3, okay, that is where x3 is greater than 0. Now, if you try to put this in terms of permittivity and permeability tensor as we have done earlier, so you can do that computation, you will see that you will get epsilon naught inverse epsilon prime to be equal to mu naught inverse mu prime given as 1 0 0 0 1 s 0 s 1 plus s square, okay. So, this basically represents a homogeneous but anisotropic medium. So, if you place this kind of a medium in the positive x3 plane, okay, it will basically give you this desired banding, right. So, this is where we started with free space with straight line optical trajectory, and then we introduced shearing along the x2 direction, okay, for the waves to bend, and then we mapped this property into the new material, and we have gone back to the old coordinate system, that is x1, x2 and x3, and that is how we do all this all the time, right. New example, like how can we do cylindrical focusing, okay. So, here also we start with parallel straight line trajectories, as you can see on the left half plane x3 on the x3 negative side, yeah. So, these are to be refracted at a planar boundary in such a way that they basically meet at a common focal point at a distance f from the boundary. So, normally this is not possible from a flat boundary between two isotropic medium, right. So, you can again think of that you start with rays with straight trajectory, and then you have to introduce some Cartesian coordinate system and then some coordinate transformation where your u1, which is x1, that is the direction in and out of this screen, that remains unchanged, but in this plane, okay, in the x2 x3 plane, you have this coordinate transformation happening. So, you can write u2 equals f minus x3 times sine x2 by f is basically the focal length, okay, and y3 will also be equal to f minus x3 cos x2 by f, and that is for the positive x3s, okay. So, once you implement this, okay, you will see that you are basically getting a kind of cylindrical coordinate system centered at u2 equals 0, okay, and u3 equals f. So, you will get something like this, So, you are basically doing a conversion to a cylindrical coordinate system which is centered here, and that is how your rays will be now converging to this particular point. So, this transformation basically converts a line that is say x2 equals a in a plane x1 equals 0, okay, that is this particular plane in the original coordinate system, into a line that is say y2 equals f minus u3 tan a by f in the new coordinate system. So, that is how it is getting this kind of a cylindrical focusing. Similarly, you can also see that what is happening to any line over here. So if you have a line x3 equals b, okay, in this plane, okay, that is basically getting converted into a circle which has got a equation of u2 square plus f minus u3 whole square to be equal to f minus b whole square. Okay. So it is basically getting converted into a circle of radius f minus b that is centered at this point where u2 and u3 are basically 0 and f. So once you understand this kind of conversion, you can always calculate the new material property epsilon prime and epsilon mu prime from this formula, okay, where the Jacobian matrix can be calculated. So once you do this, you can always practice this and find out. You obtain that epsilon naught prime, epsilon naught inverse epsilon prime, which is also equal to mu naught inverse mu prime, is basically a diagonal matrix which has got elements S 0 0, 0, S inverse 0, 0 0 S. Okay. And what is this S? It is basically F divided by modulus of x3 minus F. Okay. So that way you can find out the permittivity and permeability tensors of the equivalent media that has got principal axis along x1, x2 and x3 axis. Okay. So the principal values of permittivity and permeability tensors are dependent on the position x3, that is the equivalent material is basically graded along the x3 direction with some larger anisotropy, okay, near the focal line, as you can also see here, right. So this is how the equivalent anisotropic material that can do cylindrical focusing but back in the original coordinate system can be designed. It is little mathematically intensive. I am just telling you that with this kind of transformational optics or like coordinate transformation, you can achieve this kind of extraordinary manipulation of electromagnetic waves behavior or trajectories. So with that, we move on to the next topic, that is application of transformational electromagnetics. So the first application is invisibility cloaking. So this kind of artificially structured metamaterials have enabled this unprecedented flexibility in manipulating electromagnetic waves and producing new functionalities, something like this kind of cloak of invisibility based on coordinate transformation. So the first experimental demonstration of such a cloak was done at microwave frequencies, where normally you have a solid object, and if you have microwave sources, the rays are reflected and it is basically detected. But if you have invisibility cloak around this object, it is possible that the rays can bend around the object and pass disturbed, as if there is no material in between. And this ring is basically this kind of a structure that is made of split ring resonators, okay, that can allow you bend this path, right. However, the design cannot be implemented for optical cloak, okay, which is particularly very interesting, because in optical frequencies only the word invisibility is conventionally defined, right. So this particular image, I'll just want to tell you about this, that this particular image shows you that how a person holding a cloak can simply become invisible. That means that cloak is allowing the light rays to bend around the person and you can see the background undisturbed. So this is a kind of schematic prediction of how invisibility cloak should look like. So you can obtain invisibility cloaking using optical metamaterials. So the first thing you have to do that you use transformation based cloaking. So it basically uses a coordinate transformation to guide electromagnetic waves around an object. So the linear region that you see, that r less than b, needs to be mathematically compressed into a shell region where r is between a and b. In that case, whatever is you are keeping inside this region will be cloaked, because you are basically mapping this entire space into only this shell region, right. So, this compression results in anisotropic spatially varying permittivity and permeability values, and it will form the cloak. So, you can implement this using metal wires, okay. So, that allows you to have the physical realization, okay, of this kind of cloak. So, these are basically metal wires embedded in dielectric host, which is forming a artificial anisotropic medium. So, the wires are basically aligned perpendicular to the cylindrical surface, and the arrangement can be random. So, perfect periodicity is not required. So, that gives your fabrication little bit flexibility. So, for large scale cloaks, this metal wires can be subdivided into shorter segments, and one requirement is that the segment must remain sub-wavelength in order to ensure that you get effective medium behavior, right. So, this you can also do like this. You can take small metallic wire embedded in a dielectric host. Usually it is a cylindrical segment, but you can kind of approximate using a rectangular prism, okay, like this, and then you periodically repeat it. And these are some results from electromagnetic simulation using COMSOL multiphysics software, where you see when you put a object inside a cloak, the light rays are bent around, and after the cloaked object you will see the wavefront is kind of remaining similar. So, the object is remaining undetected. This is the magnetic field map at 632 nanometer. So, this is in optical frequency. This is the same object without the cloak being installed. So, you can see that the waves are basically getting disturbed here. So, you can identify this object if the cloak is not present. So, invisibility cloak has always been a dream, okay, for a lot of people to achieve. This idea of invisibility has long fascinated human imagination, right. So, it seemed, although confined only to science fiction and movies. However, the recent advancement in optical technology has brought us much closer to our very own real life invisibility cloak. So, here is an picture of demonstration of optical camouflage technology at Tokyo University, okay. So, as you can see, although it is not perfect, but it is kind of still telling you that you can go towards that technology with further improvement, right. It is not as sketchy as the cloaks those are shown in Star Trek or Harry Potter movie, but they are still telling you that this is the way forward. So, how does an invisibility cloak work? The visibility basically depends on the action of visible bodies on light. So, either a body basically absorbs light, or it reflects it, or it refracts it, or does all of these things. But if it neither reflect nor refract nor absorb, that means it is not doing anything to the light, and that is where it becomes invisible, right. So, we will continue this discussion in the next lecture. So, we will stop here right now for this. Thank you. And if you have got any query regarding this lecture, drop an email to this email address. Thank you.